Hey guys, in this video series we're going to be going into statistics. So before we really dive into everything and what we're going to be going over, I want to say a few things. The first is that I have spent over 10 years thinking that I was terrible at stats because I've never really been able to do probability before I really took the course. And the thing you need to remember here is statistics isn't just math, it's more of a writing course actually, and understanding how everything plays into the real world. So you'll see it a lot in biology whenever you need to run your chi-squared tests, and even in AP psychology, you'll have to use normal models, and then some elements of surveys and experiments are all covered in statistics. And for those of you that are curious or want to follow along and want extra practice, I am using the textbook shown here at the right, Statistics Modeling the World, and this one is really centered for an AP level course. But if you're also in a college course right now, this is still a really amazing resource and it's a really well written book. So statistics is a really calculator-centered course, and there are a lot of problems that you really can't do without a calculator, especially towards the end when you have to run your t-tests and stuff, but you don't have to worry about that for now. One thing you'll really need for this course is a calculator, and I know most people just have one of the scientific calculators with the basic functions. Although those are nice, there are some things that you can do on one of these graphing calculators that you can't really get on a scientific calculator, so that might be a problem for some of you. I know that this is the calculator that I personally favor, the TI Inspire CAS, but they're devilishly expensive. And so I would recommend getting one of their online interfaces. I know that one of my past teachers has used one of these before and it is very similar to the actual calculator. I am not sure where you go to download this as I have not used it, but I would recommend getting a calculator of this kind. And please bring your brains because this is going to be a wild ride. So the last thing for today will just be a quick taste of stats as a little introduction for everyone. So these two questions I do not expect you to know how to do as they go into the probability sections in chapters 13 through 16 approximately. But there's some really cool applications of stats that I think we should start off with. I know most of you are probably taking this as a part of school. So your classes, I'd say around 30 people, right? So if you think about this, everyone has a birthday because they're alive. And so the birthday problem is basically asking what is the probability that at least 2 people in your class have the same birthday. Intuitively speaking, there are 365 days in a year and there are 30 people in your classroom. Without thinking about math or anything, the probability that 2 people have the same birthday seems actually quite low, doesn't it? This is where stats gets a little counterintuitive, and this is where things get cool. So the thing about the two words, at least 2 people having the same birthday, is a bit of a problem because we're not just looking at 2 people having the same birthday anymore. There could be 2 pairs of people that have the same birthday, or 3 people that share a birthday, or 4 or 5. Maybe the whole class has a birthday and things are just freaking weird. I don't know. So these are a lot of cases that we could probably go through, and it would be really, really time consuming. So instead, we're going to do something that you'll see a lot in stats, which is taking the complement of the situation. So instead of finding the probability that at least 2 people have the same birthday, what about the probability that no one has the same birthday? So if you think about it, all probabilities end up adding up to 1. So inside of this 1, we have the probability that 2 people have the same birthday, 2 people and only 2 people, or 3 people sharing a birthday. But then all of these fall under the umbrella of at least 2 people sharing a birthday, right? So there's only one case where no one has the same birthday, and everything outside of it includes people sharing birthdays. So if we just take this, if we find the probability that no one has the same birthday and subtract it from 1, everything that's left over is going to be the probability that at least 2 people have the same birthday. Because now we've split our situation into 2 defined groups. One group is no one having the same birthday, and the other group is maybe 2, maybe 3, maybe 4 people having the same birthday. So at least 2 people having the same birthday, and that is what our question is asking. So how do we find the probability that no one shares a birthday? So let's go one person by one person. And our goal is for everyone to have a distinct birthday out of those 30 people in your classroom. So we're going to ask each person their birthday. And once one person has claimed a birthday, the person after them cannot claim the same birthday. So let's start with you. What is your birthday? So because I haven't asked anyone before you, you have 365 days to choose from. So we would write down your number as 365 days out of 365 days in a year to choose from. Now we ask your best friend sitting next to you, when is your birthday? So now that you have claimed a birthday, let's say you chose January 1st, your friend can no longer pick January 1st. So instead of 365 days to choose from, they have 364 days. Now, if we keep asking, it'll follow the same pattern. So now that you and your friend have claimed birthdays, the next person cannot choose the 2 days that you and your friend respectively took. So now they have 363 days to choose from. And if we keep going like this for all 30 people in the classroom, we will end up multiplying 365 over 365 times 364 over 365, 363 over 365, all the way down to the last person, who will be 336 over 365. So if we multiply this 30-term expression together, we will get some probability between 0 and 1. And that probability is going to be the probability that no one has the same birthday. So now that we found that, we have one more step left. We need to find the original problem, so at least 2 people having the same birthday. What we were going to do was subtract this probability, so what we got up here, from 1. So let's do that. 1 minus 365 times 364, until 336, all over 365 times 365, 30 times. Putting that into the calculator, which I will spare you from doing, trust me, it takes a long time, we get 0.7063. What this means is there is a 70.63 chance that at least 2 people in the classroom have the same birthday. That's crazy, right? Because if you think about it, intuitively, you would say that the probability is really low because there are 365 days in a year to choose from, but there's only 30 people in your classroom. And this is where the beauty of stats is. It can prove so many things for you that you would never think of in normal life. I think when I first learned about this problem, my teacher actually physically went and asked each person what their birthday was. I think about 10 people in, we got a pair, the first matching pair of the class. So that is your birthday problem. Next we have the Monty Hall problem. This one is a bit more famous actually. I have seen it in a couple movies. So it stages a scenario for you. So let's say you're on some game show. The host gives you 3 doors to choose from. Behind 2 of the doors, there is a goat. Behind 1 door, there is a car. Now the game show host asks you to pick a door, and if you pick the door with the car behind it, you get to keep the car. If not, you get a goat. I don't really see the problem with that, but I think you'd prefer the car. Let's say you get ready to choose. Which one do you choose? I'll go with number 1 this time. So the game show host, being a game show host, decides to reveal everything slowly. So instead of revealing whether your door, so door number 1, has a goat or a car behind it, he decides to open a different door. So he opens door number 3, and voila, we have a goat. So now he gives you a choice. You can either stay with door number 1, or you can choose to change to door number 2 instead. So what do you say? I've actually gotten a lot of mixed answers with this one. The first person I have taught this problem to has said to stay with the same door. And this is where I need to show you their mistake. So when you first chose a door, there were 3 doors. You didn't know which one the car was behind, so you randomly picked one. And so behind this door, there was a 1/3 chance that the car was behind it. So outside of your 1/3, outside of your little bubble here, there is a 2/3 probability floating around because all probabilities must add up to 1. So before the game show host opened a door, then each door had a 1/3 probability. So our 2/3 was split up evenly between these 2 doors. However, since the game show host opened door number 3, he eliminated the chance for that one to have a car behind it. So this 1/3 no longer belongs to this door because we know that for sure that there is a goat behind it. So what happens to that 2/3 floating around? Since it can't belong to door 3 anymore, it just goes and sits with door 2. So this 1/3 comes over here, and this 1/3 now becomes 2/3. So if you stay with the same door, your 1/3 has already been locked into place, so you still have a 1/3 chance of winning. But if you switch over to door number 2, there is a 2/3 chance that you can win a car. And that, my friends, is freaking awesome.